Hello, folks. Okay, let's pick up where we left off last time. We introduced the notion of joint probability mass functions, and we were just getting into the idea of independence of discrete random variables. So I'm going to finish this and then talk about implications on variance and talk about sums of random variables, and then we'll move on to continuous random variables today. Okay, so I hope you've been brushing in anticipation of this on your integrations and whatever you learned in the continuous realm. All right, so we had this diagram from last time, the joint probability mass function that I drew. One thing I want to point out is that these purple circles that I've drawn are actually lollipops sticking out of the plane. So we're looking at a two-dimensional axis, each representing one of the two random variables, and the probability mass function is sitting on top of this plane. So it's actually a three-dimensional diagram. The situation is three-dimensional, but the way we represent it in two dimensions is with these circles. So these circles, the values that I've put next to them are actually the heights of the lollipops sticking out of the plane on top of each of these points. So where I have, for example, 1/9 at this location, it means that there's a lollipop sitting at coordinate 1 and 1 of height 1/9. Okay? Now, last time I asked you whether these two random variables are independent, and we may have been rushed in getting to the answer. What do you think? What was our verdict, and why? Do they look independent? If any parts of the statistics of one variable change when the other random variable changes, then they cannot possibly be independent, correct? Can you see anything changing when you change one of the random variables? If I move along the x-axis and tell you x is going from 1 to 2 to 3, what can you tell me about what's happening with y? Okay, you don't want to talk to me, talk to your neighbor. Okay. Rohan, where are you? Okay. How do they change? How do the values of y change? Mm-hmm. So when x is 0, what do you know about y? Y has to be 0. So let's put that. Probability of y given x when x is 0, the probability of y being 0 is what? 1. This is the conditional probability of y given that x is 0. So if I tell you x is 0, all the probability is now sitting at the number 0. And then the probability of y given x at, say, what? x equals 1, how would I plot this? So this now depends on this is the probability, let's plot these separately. So the conditional probability of y given x is 0, is what? How would I plot that? Single lollipop at the origin of height 1. Okay? So if I tell you x is 0, y can only take on the value 0, and that's the conditional PMF. And if x is 1, what would that look like? I have 3 possible values. Are they of equal height? Yeah. If I restrict x to be 1, that means I'm looking at this column right here. Does that show on the screen when I go up and down? Yeah. And each of these were a priori equally likely, so in the conditional space, they retain their relative sizes. So if they were of equal height before I conditioned on x, they will be of equal height after I condition on x. And so these are values at 0, 1, and minus 1, and their height has to be 1/3. Why? Yeah, I divide by the probability that x is 1 in the denominator, and 1/9 divided by, well, what is the probability that x is 1? 1/3. How do I get 1/3? I sum up these 3 points. You look at your sample space, and you add up the probabilities corresponding to your event. So if the event is x is equal to 1, you look at all the points that have non-zero probabilities and add up the probabilities of those that correspond to the event, x equals 1. Those are these 3 points right here. 1/9, 1/9, 1/9. That gives you 1/3. I actually didn't have to calculate the probability of x to be able to get these lollipop heights. I could get them another way. Can somebody tell me how? What must be true in my conditional universe? Sorry, they sum to? These lollipops have to sum to 1. So 3 equal quantities have to sum to 1 in my conditional universe. Therefore, each of them must be 1/3. There usually is a multiplicity of ways you can approach these problems, and with practice, you'll get a better hang of it. Okay. So clearly, if I tell you that x is 0, your assessment of the likelihood of what y can be will be different from the situation where I tell you x was 1. So this by itself shows that these 2 random variables are not independent. So x and y are dependent. I'll also show you a little trick for showing dependence. When you have a 2-dimensional diagram like this, pick a point where the joint probability is 0, but if you were to sum across a row or a column, you won't get a 0. Okay? So if I were to, for example, pick, let's say, this point right here, 1, 2. Let's say I pick this point. I need a better color. Come on. My finger does a better job than... Okay. This hollow purple, that's the point corresponding to the joint probability at 1, 2. Correct? That's 0. Right? At 1, 2, the joint probability mass function is 0. If the 2 random variables are independent, then this equality must be true. What equality must be true? This is equal to what? X equals 1 times the probability y equals 2. To get a 0, I need at least one of these two to be 0. Is that true? What's the probability that x equals 1? Everybody. 1/3. What's the probability that y is equal to 2? 1/15. Neither of them is 0. I can't multiply 1/3 and 1/15 and get a 0. That means this equality does not hold. This is 1/3 times 1/15. Clearly not the case. So can you tell me what the general shape of a joint probability mass function for two random variables must be to have what a necessary condition is for that shape to have independence? This is triangular here. And I picked a point that was 0, and I showed that the product of the two individual mass functions is not 0. Therefore, they must be dependent. So what's a necessary condition for independence? Talk to your neighbor. That's a really fast trick to determine dependence without doing a whole lot of work. Okay, I'll take a volunteer for this one. Come on, we have a quorum. There must be some hand up. Yeah. It would be rectangular in shape, or a set of rectangles that don't have overlapping bands. Okay, so in this case, it would have to be the region of support for the probability mass function would have to be some kind of a rectangle. That doesn't guarantee that the two random variables are independent, but that's a necessary condition. You can't have holes in that rectangle. By hole, I mean points where the probability is 0, when neither of the individual probabilities is 0. Okay? So anytime you're given a PMF for two random variables where you can see that it's not rectangular in shape, or some combination of rectangles dispersed in such a way that neither of the bands overlap, then you can immediately pick a point that has 0 probability, look across, look down, compute and basically argue that neither of those is 0, therefore their product is not 0, so they must be dependent. Okay. Very good. Now, with regards to, did I do expected value of joint? No, I haven't done the expected value of sums. So basically the same rules that apply to single random variables carry over here as well. Functions of multiple random variables. So if I have a function of two random variables, x and y, that is a random variable in its own right, then the expected value of z is the expected value of g of x, y, and that is obtained by summing over all possible x and all possible y of gxy times the joint probability mass function of x and y. Okay, so everything carries over to multiple dimensions. Except here, instead of just a single sum, you have a multiple sum. You do not have to calculate or determine an expression for the probability mass function for z. Because that can get hairy. Okay? Let's see if we can... So, then if I have two random variables that are... The simplest function, of course, is a linear function. We already know that E of z is what? E of x plus E of y. But what about the variance of z? How do I compute that? Well, by definition, I know this is E of z squared minus what? E of z quantity squared. E of z quantity squared is simply obtained from these guys here. So this one is known because I know the mean of x and I know the mean of y. Now, what is E of z squared? E of z squared, isn't that just E of x plus y squared? Isn't this some function g of the random variables x and y? Okay. So let's figure this out. Tell me how to expand this now. E of x squared, 2xy, y squared. Okay, so this is E of x squared plus what? 2e of xy plus E of y squared. And so for the variance of z, I know I have to, so this is E of z squared, correct? I know I have to subtract from E of z squared the square of the mean of z. I need a z there. Okay, so E of z squared is this expression here. So let's write that out. E of x squared plus 2e of xy plus e of y squared. And from that, I have to subtract what? I have to square this, right? What's the square of that? Louder. Everybody. Do I have to define everybody? E squared of x plus 2exey plus e squared y. I apologize for the grunge. So now I subtract all that from here. So I have minus e squared x minus 2 e of x, e of y minus e squared y. What do you see emerging here? What can you tell me about these two terms? And what can you tell me about these two terms? They are variance of x and variance of y. So I have this first green blob is the variance of x. The second green blob is the variance of y. And then I have this curious thing here, which is 2 times e of xy minus e of x, e of y. So that's a formula for the variance of a sum. This quantity here has a name, and probability and statistics. It's called the covariance of X and Y. Covariance. It's a measure of how two random variables vary up to the second order. If X and Y are independent, what can you tell me about the covariance? Why are they zero? Because E of xy then becomes what? E of x times E of y. And why is that? Notice E of xy, by our definition, this is now a function of x and y. So this is the sum over x, sum over y, small x, small y, and the joint PMF, correct? Are we all here? This is g of xy. I'm summing over x and y to get the expected value, and I have to multiply by the joint PMF. If x and y are independent, what can I do to this joint PMF? I can what? Split it. So I split it. I have small x, small y, px of x, and py of y. And now what? Now this double sum looks pretty good. What can I do with it? Factor it out. I have one factor which involves only x, and I have one factor which involves only y. And what do you know about this? What is that? A what? E of x. And this is E of y. Okay, so if x and y are independent, the expected value of their product is the product of their expected values. And if you look at the covariance expression, that covariance will now become zero. Okay? This is a sufficient condition for the covariance to be zero. It turns out that you don't need a relationship between two random variables as strict as independence for this to be true. There are random variables for which the covariance is zero, even though they are dependent. In general, when the covariance of two random variables is zero, we call those random variables uncorrelated. So independence implies uncorrelatedness, but the opposite is not true necessarily. So two random variables can be uncorrelated but not independent. I won't go into the details of that right now. We'll get to that in a few lectures. So if x and y are independent, then the variance of z, and we define z as the sum of those two random variables, then the variance of z is simply the sum of the individual variances. And that's really nice. With expected value, it doesn't matter whether the random variables are dependent or independent. The expected value of a sum is always the sum of the expected values. With variance, it does matter. So the moment you go to second order properties and expressions, you have to take into account the dependence and independence of random variables. All right. Any questions on what we've done so far? Okay, let's go back to an example we did a while ago, the hat problem. N men with N hats. Remember that problem? N men walk into a party, they hand over their hats to the receptionist. The receptionist is klutzy, randomly assigns hats to people on the way out. So, for that problem, we defined an indicator random variable, which means if ith man gets his hat back, otherwise, it's zero. What was the probability on the one branch? 1 over n. And this is 1 over 1 minus n. And in the other lecture, so the total, so we now define x as the total number of these guys who get their hats back. Total number of these men who retrieve their hats correctly. And last time we found the expected number to be what? 1. Well, not the last lecture, but whichever lecture it was where we developed this. So now I want you to figure out what the variance of x is. Darn. With the expected value, it was easy, right? Because the expected value of the sum is the sum of the expected values. So I want you to talk to each other and see if you can find a way to calculate the variance of the number of people who get their hats back. You may want to start with the expression x squared and use some algebra. So what is x squared? Let's get you started so you don't bang your head against the wall for the next several minutes. X squared is what? Sum of the xi squared plus basically xi xj, where I is not equal to j, right? J, thank you. Yeah. So, this one should not give you trouble. How is xi related to xi squared? They're identical, right? Xi takes on the value 1 with probability 1 over n, takes on the value 0 with 1 minus that probability. Well, xi squared is exactly the same as xi. Whenever xi is 1, xi squared is 1. Whenever xi is 0, xi squared is 0. Okay, so that's easy. That's just the second moment of a Bernoulli, and you add up n of them. The trickier part is this one. So I'll work on that. Scoot up. How far? The whole problem is right here, unless you want to copy something else. How many of these terms do you have? And how do you get n squared minus n? N squared minus n is n times n minus 1. Yeah, or you can think about it as n choose 2, but you've got a 2 in front of these. You can write this as 2 times xi xj, okay? So this is n choose 2 times 2. So you've got n times n minus 1 terms here. And so your focus should be, what is e of xi xj? Isn't this some function g of xi and xj? Yes or no? So we're looking at the function of xi xj, which happens to be the product of xi and xj. That's the random variable whose expected value I'm trying to find. And so then this is all the values of xi and all the values of xj. Xi, xj, p of what? Xi, xj. This law of expectation invariance will haunt you for the rest of your life. You've got to get used to it. So it just raises its head under various functional pretexts over and over and over. So here we have the expected value of some function of these two random variables. So to figure out what that expected value is, you have to look at the product, which is that function, and their joint PMF. So focus your attention on what are the terms, what is required for each of these terms to be non-zero? What must happen with the ith guy and the jth guy? Both have to be 1, right? So the only terms that matter are those terms where small xi is 1 and small xj is 1. Both of them have to retrieve their hats. What is the probability of that happening? Remember, they're not independent. I could have put this on an exam problem, so make use of your buddies in the class or your neighbors to figure this out. It might involve a little head scratching, but with a little care, you should be able to figure this out. I want the ith guy. If I tell you that the ith guy got his hat back, what can you tell me about the probability that the jth guy will get his hat back? What's the probability that the ith guy will get his hat back? 1 over n. So now I tell you, so basically what I'm asking you to do is look at this xi, xj, xi, xj, and we're writing this in terms of the conditional probabilities. That's what we're doing. Right? J given xi. So instead of writing the joint, this is how I'm figuring it out. The probability that the ith guy gets his hat back is 1 over n. You've already told me that. So given that the ith guy has already gotten his hat back, given that xi is 1, what's the probability that the jth guy will get his hat back? 1 over n minus 1. Wow, you must have an excellent probability instructor. Okay. How many of these terms do you have? N times? N minus 1. So what's the answer? Give me a final answer now. So E of x squared is n of these guys. So what is this first term? What's the second moment of a Bernoulli? So xi is 1 with probability p, 0 with probability 1 minus p. What's the second moment? It's the same as, so the second moment is the same, because xi squared is the same as xi. You've already told me this. So this is p. So I've got np here, plus what? Oh, what is that p? 1 over n. So let's put that down here. N times 1 over n. It's not just some arbitrary p. It's 1 over n. Okay. And what's the second term? You told me there are how many terms? N times n minus 1. Times this guy here. 1 over n times and minus 1. So what's the second moment? These cancel. These cancel. You get 2. And what's the variance of x now? Sigma x squared is the second moment minus square of the first moment, or the mean. Second moment we just figured out was 2, and the mean was what? So its square is 1. So that's also 1. Isn't that amazing? It looks like a very complicated problem, and you got to keep things in keep the accounting of the permutations and combinations in your head straight, and the random variables are not dependent, but the answer is beautifully simple. So the mean of the number of people who get their hats back is 1, and so is the variance. Notice, we're not even talking about what the probability law is governing x, the total number, who get their hats back. Okay, that's the beauty of doing these kinds of first and second order analyses with random variables. By first order, I mean expected values of linear functions of the random variables, and by second order, I mean terms involving the second moment, which include the variance. Okay. I think I'm done with that. Any questions? All right, I'll give you a 2-minute break, and then we're going to do this sum of independent random variables and how to determine the probability mass function of that sum. And then I'll move on to continuous random variables. All right, take a break. Okay. So I've got 2 random variables, x and y. I create a third random variable, which is the sum of these 2. And I want to know, can I describe the probability mass function for the sum of 2 independent random variables? So z is my new random variable, obtained from summing x and y, and I'm interested in z. We can treat this the way we treated events in the earlier part of our probability discussion. So I can write this as the set of joint PMFs where, say, if I tell you that random variable x is small x, and I'm going to sum over all possible values of x, what should y be for their sum to be z? What should I put here? I'm adding up all the possible points in the two-dimensional plane, xy plane, where x plus y is equal to z. Here's my two-dimensional plane. Here's x. Here's y. Can you show me how to draw the line x plus y equals, say, 2? What would that line look like? I want the sum of these two random variables to be 2. What kind of line would I draw? Yeah. Yeah, through this point corresponds to the sum being 2. This point corresponds to the sum being 2. Those are the only 2 points I need to draw the line corresponding to all the points being 2. So this is the z equal 2 line. That's where x and y are 2. So one way to find the probability that that z is 2 is to add up all these point probabilities, correct? Huh? Isn't that the case? Isn't every single point on this line, doesn't it correspond to z being 2? Yes or no? Okay, now if this is some arbitrary value z, then this zero crossing would be small z. This zero crossing would be small z. So one way I can add up all these values is to index through x. That's what I've done here. So I'm going through all the values of x. So if random variable capital X takes on the value small x, so if this is x, what is this value here? Z minus x. Z minus x. Are we all here? This is the trickiest part of the whole discussion. After this, it's downhill. The random variable capital Z takes on the value small z whenever and wherever random variable x takes some value small x and the other random variable y takes on the value, the difference of z and x. Because remember, if z is equal to x plus y, then y must be z minus x. What can you tell me about this sum? What do I know about x and y? Huh? What was the premise of our whole discussion here? They're what? They're independent. So what can I do with that? Knowing that they're independent, what can I do with this joint PMF? I use the product rule. So the joint probability mass function must be the product of x taking on the value small x and y taking on the value small z minus x. If you ever take a course in signal processing, you will immediately recognize this as what they call the convolution of these two functions, px and py. This is the convolution. You don't need to worry about the name here of px and py. But this is how it's defined. You take one function and you take the other function. You've got a dummy variable x. You flip and shift the other function, multiply and add. We'll do an example. Actually, it'll help you on your homework, so you've got to be on your toes as I walk you through some of that. But this operation here is called the convolution of these two functions. I could have started with the sum over the random variable y, in which case I would have had a y here, p of x, y, y takes on small value y, and x takes on value what? Everybody. Z minus x. Z minus y, sorry. Thank you. Just checking if you're awake. Just checking if I'm awake. And because they're independent, I can write this in separate form. And this would be the convolution of py and px. I use the star symbol to denote convolution. Normally it's an asterisk. But because these two represent the same thing, convolution is essentially a commutative operation. Whoops, I don't want the star there. Star py is the same as py star px. The best way to see how this works is through an example. So let's do that. So the example is from your homework. I've got random variable x, which is Poisson with rate lambda, and I've got random variable y, which is Poisson with rate mu. What this means is that the probability mass function for x is what? What to the what over what factorial times e to the what? Those are, see, you should record these. You should use these at your frat parties or sorority parties. You know, you go walk up to a person and say, what to the Poisson is what? They're probably from the French department. They'll tell you it's a fish. Talk to me, people. The clock is ticking. You don't want me to turn into a martyr. If I don't get to continuous random variables, your TAs will send me to the slaughterhouse. Lambda to the x over x factorial e to the negative lambda. And the same is true for y. So that one is mu to the y, small y, e to the minus mu over y factorial. Okay? So, come back. All right. So now we have a random variable z, which is the sum of these two. And we want to figure out, and they're independent, so x, y independent. This looks like a toy problem, but actually it has practical applications. So later on when we talk about random processes, and I bring back the Poisson from the dead and talk about Poisson arrivals, so packets arrive at a router according to a Poisson random process, at an average arrival rate of lambda per second, and through another channel, packets arrive at the rate mu. You want to figure out what's the total number of arrivals and what's the probability law governing the total number of arrivals. If these two streams of packets that are arriving at a router, each behaves according to an independent Poisson, how can I model the overall arrival of packets at the router? And you can think of, there don't have to be packets and routers, there can be people arriving at a stoplight, there can be cars arriving at a particular location, whatever queuing situation you're in. It turns out that Z will also be a Poisson random process, and its average arrival rate will be the sum of the individual ones. And that's what we're going to show. Okay? So, talk to me. Get me started. PZ of Z is what? Convolution says, do what? P, X, can you give me a range for X? 0 to Z. If the total number of arrivals, if Z is some positive number, well, what values can Z take? Actually, I should ask you that first. X and Y are both are both what? Positive, negative? Huh? If x is Poisson, this is valid for what? We said there's a unit step function here, right? It's only each of these is non-negative. So I add two non-negative random variables, I get another non-negative random variable. So x will go from 0 to whatever the total number is. Correct? If I want the total number of packets arriving to be z, then x cannot exceed z, and x cannot be less than 0. So this sum goes from 0 to z, and this is times what? P of y times what? Z minus x. That's what convolution sum says. Okay, well let's do that. X goes from 0 to z, and px of x, you know. It's lambda to the x over x factorial e to the minus lambda. And py of z minus x is what? What over what times what? Mu to the z minus x over z minus x factorial times e to the minus mu. If my claim or hunch is correct that the sum of these two Poissons will be another Poisson, are you seeing inklings of that emerging from this expression? What exponentials are you seeing? E to the what? Minus lambda plus mu. You see that, right? From here and here. That's a good sign, because I got my exponential already. And let's see. Now I have a sum, x from 0 to z, lambda to the x, mu to the z minus x. I've got, what do I have? I've got an x factorial, I've got a z minus x factorial. What do I need in the numerator to make this pretty? Huh? Z factor. If I put a z factorial here and divide by a z factorial, then this looks nice, huh? What would that be? Z choose x. Okay. Wow, you must have had a great combinatorics instructor. I should tell Satish that. So far, I've got my e to the minus lambda plus mu. I've got my z factorial. So I've got two of the ingredients for the Poisson already sitting there. What am I missing? This is z choose x. X goes from 0 to z times lambda to the x mu to the z minus x. What does this look like to you? Binomial. So this is equal to what plus what? To the what? You must have had a terrible combinatorics instructor. What? Lambda plus mu to the z. That's from the binomial theorem. You're raising a sum of two things to the zth power. That's what this whole sum is. We're done. Yay! Cool. So I've got my lambda plus mu to the z. I've got my z factorial, and I've got e to the minus lambda plus mu, and this is true for z equals 0, 1, 2, and so on. Well, that means z is a Poisson with parameter lambda plus mu. So if I'm a router, packets come from one end at rate mu per second, they come at the other from another channel at rate lambda per second. The overall rate of packets arriving, provided these two are independent streams, is simply obtained by adding the arrival rates. The nature of the probability law stays the same. There aren't that many probability laws that follow this kind of a property where you add two independent random variables following a certain PMF, and the sum is also in that family of PMFs. Rohan, you have a question? This summation? So A plus B to the n is n choose I from 0 to n, A to the I, B to the n minus I. Isn't this the form of the binomial you studied? So here your n is z, A is lambda, B is mu. It's only the symbols that have changed, but this is the binomial theorem. In fact, they give you that hint in the problem statement. So I just solved the problem, homework problem for you. You owe me. All right. Any questions on what we just did? Sum of independent random variables. If you want to figure out the probability mass function, you simply do the convolution of their individual probability mass functions. You may want to go home and practice adding two uniform PMFs or uniform random variables and see what kind of a shape you get for the overall PMF. So that's a good exercise for you to get some more practice with convolution. All right, I have bad news for you. We're going into the world of integrals and nasty continuous stuff. I'm going to extricate you from your discrete world cocoon. By the way, I've had several requests for these notes, my chicken scratch handwriting on the screen. Is that really something you want? It comes with no warranty. So because I won't be editing it, I'll just be dumping this into a PDF file and making it available. Is that really what you want? Okay, but I'll do that if you give me one promise. That you watch the videos. Okay? More than once. Because I don't want this to be a substitute for your engaging with the video lectures. That you have to do. Some of my best students in all these years that I've been teaching are those who go and engage with the videos of the lectures more than once. Especially in those lectures where the topic gets a little hairy and you really need to slow down. In some places, you may want to play me at 2x speed. But rumor has it that John De Niro actually slows down his speech deliberately because he knows that people watch him at 2x. I haven't verified this. I have to ask him. But that's the rumor. I don't have the talents that he has. But please, do watch the lectures. I'll make available these PDFs. I try to go as slowly as I can, and I write for a reason. I don't use slides usually for a reason, because the reason is that I want you to be able to follow. So I don't want you to be scribbling all over the place. That's why I think if you pay attention to what we're doing in class and then going and watching the videos and then taking notes or cleaning up your notes, that's a better plan. Okay. I have a Wheel of Fortune uniformly calibrated from 0 to 1. Okay, I spin this and I give you that amount of money. Uniform Wheel of Fortune. What's the probability that you'll get $50? What? Is it a half? Give me some number, any number. 0. Why? Yeah. How many points in my sample space? Huh? Infinite. What kind of infinite? Not all infinities are the same. Uncountably infinite set of points in my sample space. So the probability that the wheel will land at any particular exact number is 0. So we need a different mechanism to describe what is happening. We still have a random experiment here, a random trial, but there is a different way to describe the situation. Is it, if I ask you what's the probability that you'll land between 1/2 and 1/2 plus dx? It'll be dx. So the outcome can be anywhere from 0 to 1. This is the outcome of the experiment. And if I give you a sliver and I say, what's the probability that it's between x0 and x0 plus dx, or x1 and x1 plus the same dx, how would you compare these events, the probabilities of these events? They are the same. And that's why we have a uniform function that is 0 everywhere except here, representing the probability. But it's not the same as the probability mass function. We use small letter f for this. This is called the probability density function. And as I develop this story, you'll appreciate why we call this a density. This happens to be a uniform probability density function. Now, why do we call it the probability density function? Before I do that, I want to introduce you to another function which is easier to grasp and which actually we can use to talk about not just continuous random variables, but also discrete random variables. And that's the cumulative distribution function. So we represent that with a capital letter F. This is the probability that random variable x is smaller than or equal to small x. Okay? Now, if we look at the uniform wheel situation, can you give me some of the values for this f of x? What happens if I take the limit as x goes to minus infinity? This is the probability that x is less than or equal to minus infinity. What is that? Everybody? 0. Because minus infinity is as low as you can get. What's the limit as x goes to plus infinity? This is the probability that x is less than or equal to plus infinity. What should that be? 1. Okay. If I ask you what's the probability that x is between between b on this end and a on this end, can you write that in terms of the cumulative distribution function? Talk to each other. When in doubt, draw. Here's the x-axis. Here's B. Here's A. And I'm asking you to figure out what this probability is right here. In terms of the cumulative distribution function. Any ideas? Let's see if I can find better. Let's try this one. It's what? F of B is what? Everything to the left of B, right? Including B. And F of A is what? Everything to the left of A. How do I get the red region from the blue and the green? I subtract. Go back to my black color here. So this is the probability that x is less than or equal to b minus the probability that x is less than or equal to a. Well, this is exactly fx of b minus fx of a. So what we have is that the probability that a is less than x, less than or equal to b, is the difference of these two. What does that say about the way this CDF behaves as you increase its argument? If a is less than b, what can you tell me about the relative sizes of fxa and fxb? If a is less than or equal to b, which one's less than which one? F of b is greater than or equal to fx of a. I know that because when I look at this equation, the left-hand side is a probability, correct? And because it's a probability, it has to be non-negative, which means this term must be greater than or equal to this second term. So whenever you have an argument in the CDF which is less than or equal to another one, this inequality must hold. What this means is that the CDF is a non-decreasing function of x. The CDF, I mean this function. So, can you tell me how to draw the CDF for the uniform? This is the uniform. What's the CDF for this? What's the probability that x is less than 0? Less than or equal to 0? Zero. So if this is 0, to the left it's 0. What about to the right of 1? What's the probability that it's greater than 1? 1. This is 1. And how does it behave in between? What's the probability that it's 1/2? Or, I'm sorry, yeah, what's the probability that fx of x is 1/2? In other words, I spin the wheel and I get some value less than or equal to 1/2. 1/2. So how does it behave from here to here? Linearly. Okay? So that's the CDF for this function. Okay. Now, let's go back to my black ink here. Now, suppose I ask you what the probability is that the random variable x is between small x and x plus dx. What would you tell me in terms of the CDF? So I'm not talking about the uniform anymore. In general, I want random variable x to be somewhere between here and an infinitesimal interval to the right. How would you write this in terms of the cumulative distribution? We already did it for A and B. So what's my A here? And what's my B? So what should I write on the right-hand side? It's what minus what? X plus dx minus f at x. Correct? All right. So what I'm going to do now is divide each side by dx. What does the right-hand side remind you of from Mr. Rogers' calc? Well, we're not there yet, but what does this look like? This what? If dx is small enough, it's the what? Derivative of the cumulative distribution function. Notice what's sitting on the left-hand side. The left-hand side, I have in the numerator a probability. In the denominator, I have something that's in the units of the random variable. So if the random variable is meters, then the unit of the denominator is meters. So I've got probability over the unit of the random variable. Does that make sense now why we call this left-hand side a density? It's a density of probability, right? Mass per unit length, mass per unit time. It has the features of a density. Here, you have probability per unit of the random variable. So this nice relationship exists between what I described as the PDF, probability density function. How much probability is concentrated per unit length or per unit of the random variable in question, whatever that unit is. So this is one way to look at the relationship. Now, not always is the CDF continuous or differentiable. And in those cases, you've got to be careful about how you interpret this derivative. But there's another way to think about this, which is that fx of x minus fx at minus infinity can be written as this. And what do I know about this one? 0. So this is another way to represent the same relationship, but in integral form. Wait a minute, I need a dummy variable here that's different from x. Go away. Okay, it wants to be lambda. Lambda. Bill Gates. I need to break out my iPad. Okay, so the CDF is essentially the integral of the PDF. These are the two salient relationships between the cumulative distribution function and the probability density function. So we've talked about the non-negativity of the CDF. We've talked about the fact that it's 0 at minus infinity and it grows to 1 at plus infinity. There is a subtlety with PDFs that didn't exist with their discrete counterpart. We still need the PDF to be non-negative. What can you tell me about this here? Can you write this in terms of the CDF? Looking at this expression here. Isn't that just fx at infinity? And what is that? 1. So the PDF must integrate to 1, just as the PMF, its discrete counterpart, had to sum to 1. But we do not require that the PDF be less than or equal to 1. This is somewhat counterintuitive. PDFs can blow up at certain points. As long as they're non-negative and as long as they integrate to 1, you've got a valid PDF. So I'll just give you an example of that. This is a valid PDF. 1 over 2 square root of x for x greater than 0 and less than or equal to 1 and 0 elsewhere. This is non-negative, and if you integrate it, you get 1. This is a valid PDF, but it blows up at 0. Is it a useful PDF? Not really. Here's a useful PDF. Lambda e to the minus lambda x for x greater than or equal to 0 and 0 elsewhere. This is called the exponential PDF. And it looks like this. And at 0 it's what? Lambda. And lambda is assumed to be a positive quantity here. Otherwise, you'll run into trouble. Does this integrate to 1? If I integrate from 0 to infinity, it's 0 on the left side. But if I integrate this, I get what? I get minus lambda in the denominator, e to the minus lambda x, and it goes from 0 to infinity. What does it evaluate to at infinity? So I've got lambda over minus lambda. At infinity, it's what? What does this exponential evaluate to at plus infinity? 0. Minus, what does it evaluate to at x equals 0? 1. So that gives you what? 1. So I've got a non-negative function. It integrates to 1. I've got a valid PDF, and it turns out to be a very important PDF. Okay? And I'll talk more about some of its properties in the future. This exponential is the continuous counterpart to the geometric. So expect the memoryless property showing up soon. Bye-bye. I've got office hours at 2:30. Show up. Don't let me hang to dry. There are enough of you to have a nice conference room filled up.
How are you?
No, not bad.